Very good morning, my dear students. Today we are going to focus on the laws of thermodynamics and overview, which means we have three different laws of thermodynamics, and particularly for our stream under the chemical engineering, the laws will be have the similar statement when compared with the mechanical engineering stream, but the application or the approach of these laws will be different for our case. That is what we are going to focus under the chemical and thermodynamics course today. Let us first understand the first law of thermodynamics. As we are all well known that nobody can create the energy or destroy the energy, which means the total energy of the entire universe, particularly for our planet Earth, remains constant. That's why always we focus on the energy transformation or the energy conversion, which means energy can be converted from one form to another form or transformed from a system to the surroundings or the vice versa, because this we call it as a law for the conservation of energy. Because the thermodynamics stands for the flow of heat. So heat is measured in terms of the energy and the energy transformation with respect to the temperature as well as the change in the temperature. So how do we understand this, or how do we approach such a first law of thermodynamics? There are two processes. One is said to be spontaneous, we call it as an instant one, and another is the process with respect to the time, because the spontaneous means a time t equal to 0. So the spontaneous processes are those that can proceed without any outside intervention. What does it mean? There is no effect of the surroundings to a system. Whenever there is a physical or chemical or biological changes happen in a system, we say it as a process. Right? So let us consider the simple example to understand the spontaneous process. I have shown in the picture there are two vessels A and B. In the vessel B, a particular gas is filled completely, say under atmospheric conditions, and B is an evacuated one, say an empty one. So there is a connecting wall in between the A and B. When I open that wall, instantaneously the gas will effuse into vessel A. But once the gas is in both the vessels, okay, both the vessels are filled, up to that we can say the process is spontaneous. Okay, once both the vessels are filled and equally balanced, say half atmospheric pressure in both the vessels A and B, on the reverse direction, such process will not be considered as spontaneous one. So a process is spontaneous is in one direction will not be spontaneous on its reverse direction. That is the concept. Likewise, if you see uh, the position of a material, say needle is here, okay. So the position, if you see, well, it is being grounded and it is being affected by typical cause of corrosion. Okay, with respect to time, the change in the outer surface being corroded is said to be spontaneous in one direction. But in the reverse direction, we cannot say it as a spontaneous, it becomes non-spontaneous, because whenever the corrosion is happens by a natural means we can say the process on the surface of the needle as a spontaneous. But a corroded metal or the needle shown here, if you want to clean it, means it is not spontaneous. We have to add either some other solutions to remove the corroded portion or the corroded surface, or we have to wipe it out with ourselves. So, in the reverse direction, it needs an additional process. That's why it is not said to be a spontaneous one. Understood? Likewise, if you see with respect to the water, the process that are spontaneous at one temperature may not be spontaneous at other temperature. What we have seen in the first, the position, the equilibrium. Second, the direction. Now the process is being understood with respect to temperature, either spontaneous or non-spontaneous. Say for example, the water. So the water is spontaneous in both the direction. The water is spontaneous in both the direction, which means above 0 degrees Celsius, it is spontaneous for ice to melt. Correct? It's a natural phenomenon. If we keep an ice on an open surface, when the surface temperature is or the atmospheric temperature is more than 0 degrees Celsius, definitely it will melt. And below 0 degrees Celsius, the reverse process is also spontaneous, which means if we keep that surface, the water, on a surface or on open atmosphere, which is having 0 degrees Celsius, more than 0 degrees Celsius, naturally the liquid phase of water begins to melt. It is spontaneous. Got it? Likewise, when you see the reversible process, which means the next category is the reversible and irreversible processes. For a reversible process, if we focus, the system changes in such a way that the system and surroundings can be put back in their original states by exactly reversing the process, which means the changes in temperature or any changes in that process are infinitesimally small, which means negligible change in the variables of such process. That's how it is shown. Either there is an interaction of a system with the surroundings or the surroundings with the system with respect to the change in temperature. If you focus, okay, the change in the temperature will become zero. Then your system and surrounding will be considered as a reversible process. Likewise, it is shown in a piston and cylinder action where a gas is filled through a known portion or compressed through a piston, so that there will be a vacuum in the other part with respect to the movable partition. When the partition is open, then the gas will fill the entire piston or the cylinder. So the work or the energy will be considered with respect to the movement of the piston through the movable partition. In such cases, the gas and the process of the gas inside a piston and cylinder will be considered as an irreversible one, which means irreversible processes cannot be undone by exactly reversing the change of the system. it is impossible. So, all spontaneous processes are irreversible. All real processes are irreversible. Understood? So, this will signify the difference between the reversible and irreversible processes. So, as we begin to understand the first law of thermodynamics, all spontaneous and real processes are always irreversible. Got it? Now, let us move on to the concept of entropy. Before defining or clearly understanding the second law of thermodynamics that is applicable for our engineering stream. So, who coined up this entropy? Rudolf Clausius, a well known German scientist in the 19th century. He only coined up the concept of entropy. Clausius was convinced of the significance of the ratio of heat delivered and the temperature at which it is delivered. Which means the ratio of Q over T will play a vital role and gives the importance to understand the second law of thermodynamics. That is what Rudolf Clausius was convinced about the significance of Q over T. So, what is entropy then? After this, entropy can be thought of as a measure of the randomness of a system. Generally, it signifies the degree of randomness because if you see the gaseous particle when compared with the liquid particles, we can streamline the liquid flow. Or when the liquid is contained in a system, we can clearly understand the nature of the liquid. But a gas or the molecules of the gas, you cannot point out the direction of the movement where it is being contained or handled, which means the molecules in the gas will move here and there like a zigzag or whatever it is more than the liquid molecules. So, the measurement of the randomness movement of the gaseous molecules will give us an idea for the concept of entropy. That is what Rudolf Clausius convinced. And it is related to the various modes of motion in molecules. I mentioned, no, it will move here and there uh, more than the liquid particles. So, the entropy is directly related to the various modes of motion in molecules. And if you see the nature of entropy, like the total energy and enthalpy, entropy is a state function because you cannot define the path for it, or you cannot visualize or understand the path for it. Therefore, change in entropy will be considered in similar to the change in the total energy as well as the change in the enthalpy. Nothing but change in entropy is equal to its final value minus its initial value. So entropy for a process occurring at constant temperature, that means for an isothermal process, is well defined as the ratio of heat that is transferred when the process is carried out reversibly at a constant temperature with respect to the temperature measured in Kelvin. Lord Kelvin is a lord for the heat and the heat flow engineering. That's why we always honor him with the temperature measured or the measurement or the handling of temperature in any engineering aspect in Kelvin only. Particularly when we consider the international standards or the meter, kilogram, second, uh, MK system of measurement temperature, we always consider on the Kelvin measurement. So if you see the definition for the change in entropy, particularly for an isothermal reversible process, this is how we consider. So we have to consider the heat that is transferred when the process is carried out. See, there is a simplest difference between thermodynamics and heat transfer. Thermodynamics is a unique one which will not measure the quantity of heat with respect to the direction or with respect to the time, which means the time constraint in thermodynamics is not well defined. But in the heat transfer, we always focus every measurement of heat or the transfer of heat with respect to time only, which means in thermodynamics, energy is accounted directly, but in heat transfer, its equivalent power is accounted. Got it? This is the simplest way to understand uh, the thermodynamics and the heat transfer. Okay. Now let us define the second law of thermodynamics. After knowing what an entropy and how it is being convinced by Rudolf Clausius and how it is being affected by the parameters like the temperature or the various motion of the particles while the particles under movement. So according to the second law of thermodynamics, the entropy of the universe does not change for reversible process. Entropy of the universe does not change for reversible process and increases for spontaneous process. This is the statement of the second law of thermodynamics and how we have to see in our chemical engineering. Because when you compare with the mechanical engineering, the concept of thermodynamics is similar, but they always think about how the heat is transferred with respect to a source and a sink. Based on that, they will define a heat engine and heat pump. But for our case, we have to focus on the entropy and its measurement that will give us how much amount of free energy or the standard free energy that we need to run our chemical processes or our chemical reactions that might reach an equilibrium condition. In that case, we have to focus on the entropy and its relation with the free energy. Got it? So, the entropy of an universe does not change for a reversible process and increases for a spontaneous process. And there is another limitation which is highlighted below that statement. But entropy can decrease for individual system. Understand the system and the process. Already I told system is a physical matter or anything. But if a system undergoes any change in that physical matter or chemical or biological matter, we will treat that system as a process. Understood? Okay? So, based on that, we have to understand the second law of thermodynamics. Got it? Which the mathematical way to express The second law of thermodynamics is this one. For a reversible process, particularly an ideal process, the change in the entropy of the universe is zero. That's what its statement is said very clearly. You cannot change it and you cannot break it. That means change in entropy of the system along with the change in entropy of surrounding will be equal to zero. But for an irreversible, real or spontaneous process, the change in entropy of the universe as a sum of the system and surroundings will be greater than zero. But what I said, for individual systems, the entropy might decrease, which means the change in entropy for an individual system might be less than zero, might takes a negative value. As I mentioned before, giving the statement of the second law of thermodynamics, the molecular motion will have a greater significance in the entropy and its entropy measurement. That's what we are going to focus further to understand the importance of the second law of thermodynamics and further the third law of thermodynamics. Ludwig Boltzmann, a well-known physicist, described the concept of entropy on the molecular level. The simplest way to understand is the temperature is a measure of average kinetic energy of molecules in a sample. That is how he described his theory. Temperature is a measure of the average kinetic energy of molecules in a sample. Okay, that's how the picture also shown. The vibrations, the rotation, which means the energy due to vibrations, rotations of the molecules in a sample will account the measurement of temperature. That's how our body temperature will also change. Whenever we are actively doing any physical activities, okay, say running, jogging means, definitely you can feel there is a change in the temperature, and based on the activity you made, you can understand how the body temperature changes. As I mentioned before, the molecules exhibit several types of motion. One is the translational. That means movement of the entire molecule from one place to another. Then vibrational, you know it. Periodic motion of atoms with a or within a molecule. And rotational motion, rotation of molecule on about an axis or rotation above the sigma bonds. The most common physical bond will give us the structure of a particular molecule. Translational means the movement of that molecule, if you see it as an object, from one place to another place. That is considered as translation. Vibrational, when a molecule get vibrated or the atoms of the molecule get vibrated, when there is a change in the physical state of that molecule. Which means, say if you are heating a metallic surface, okay, by a known source of fire, right, then the atoms which is structured or organized in that metal will receive that heat and vibrate. Based on that vibration only, it transforms the heat from its state to the neighboring atom. That is how it is continuously transferred, and at one stage it reaches the uniformity on the entire surface. This is how the temperature distribution on a surface will be considered. That's why it is said a periodic motion of atoms within a molecule at one stage will reach us the uniform distribution of the temperature. Got it? Then the rotational, you know it. At a particular point on an axis, the rotation will account based on the strength or the nature of the bonding. Got it? So these are the most three different types of molecular motion which will be accounted to measure the entropy on the molecular scale. That's how Boltzmann envisioned the motions of a sample of molecules at a particular instant in time. This would be akin to taking a snapshot of all the molecules. He referred to the sampling as a microstate of the thermodynamic system, which means he defined the state because entropy is a state function in a microscopic view because we cannot see the entropy as a macroscopic one. So each thermodynamic state has a specific number of microstates. So that is what the measurement of the microstates was experienced by Boltzmann. Okay, so based on that, entropy is defined as k times logarithm of number of the microstates, or the entropy is directly proportional to the logarithm of the number of microstates of each molecule. And the proportionality constant is said to be the Boltzmann constant. You can see it's how many 10 raised to the power minus 23. It is multiplied. 1.38 is multiplied by 10 power raised to the power minus 23, which means the specific number of microstates will be equivalent to the 10 raised to the power 23 or more than that. Then only the entropy will be a positive quantity because logarithm of more than that value will accounts the microstate number of microstate will accounts the entropy as a positive quantity. Okay, very clearly understand. Only for individual system the entropy decreases, not for the processes. Either it reaches zero for the universe for a reversible process, or it will be greater than zero for a irreversible real and spontaneous process. So this is how Boltzmann accounted the measurement of entropy. Got it? The implications on a molecular scale is highlighted here. If there are more particles means there are more states, then more entropy. If there is a high temperature existence means then there are more energy states, then more entropy. And the molecule is less structured means when you compare with gas versus solid, gases are having less structure means they have more states, which means more space for the movement of the atoms. Or then there will be more entropy. So based on this, the number of microstates and therefore the entropy tends to increase with increase in temperature. Space will account the volume and the number of independently moving molecules, small n. Hope you understand that one. Or the number of independent moving molecules will be again said to be in a way of accounting the Avogadro number also. So all these things, the increase in the temperature, the volume, the number of independently moving molecules will account the increase in the entropy. Okay, that's what mentioned with respect to the physical state also. Entropy increases with freedom of motion of molecules, which means if the molecules are more spaced, then if you given motion, either naturally or artificially, the freedom of motion of molecules will increase the entropy. Therefore, if you check which are all having more space between the atoms or the molecules, as we know that solids are rigid, confined. So the freedom of motion will be very less when compared with the liquids. They have a slight relaxation that we can monitor the movement of molecule in a liquid along a streamline. But when you compare the freedom of motion of such molecules of liquid with the gases, the gaseous state or the gaseous phase or the gases will have molecules of having more free space to move here and there to account the randomness. That's why the entropy of the gases are always greater than the liquids as well as with the solids. That is what the simple mathematical relation explains with respect to the physical state. Now, when you come to the solution, our area, dissolution of solid. You all know that ions have more entropy, which means they have more states. But when you say with some water molecules, have less entropy because they are grouped around ions. That's what shown in the our diagram or the figure. So usually there is an overall increase in entropy. The exception is very high charged ions that make a lot of water molecules aligned around them. These are all exceptional case. Okay, generally the ions have more entropy because of their more states in nature. Got it? So a solution is made means we need the combination of both anion and cations, like the positively charged and negatively charged ions. Okay, right? So in solutions, how the entropy changes? In general, entropy increases when gases are formed from liquids and solids. Understand? When gases are formed from liquids and solids. Dissolution or sublimation, if you see, a simple example is a sublimation. In that case, entropy will increase. Okay, or the next thing is liquids or solutions are formed by solids. Also will increase the entropy. What is that one? Simple. Melting of ice. You can understand. Will increase the entropy. The number of gas molecules increases the entropy. Well known. Already I told. The number of moles. Already I told. The number of molecules also will increase it. If you see the first two cases, the sublimation will be considered. Or what you can say, when you heat a particular solid also, it will melt. Sublimation, melting, all will account the increase in entropy. Understood? Based on having such informations about the change in entropy and the molecular scale of measuring it and the physical state of accounting it, now let us define the third law of thermodynamics. What it says is the entropy of a pure crystalline substance at absolute zero temperature or absolute zero Kelvin temperature is zero. What it means? A pure crystalline substance will have the W value. The W value. What is W? Number of hope you understand that one. The number of randomness or the number of movements to account its molecular state. Got it? that is 1 in a pure crystalline substance, because its existence of physical matter is 1. So the W value is 1. So the logarithm of 1 is 0. And K is the Boltzmann constant, you know it. Got it? So this is how the third law of thermodynamics will be viewed in our engineering. The entropy of a pure crystalline substance exists in a single matter having the W value 1 at absolute 0, which means the temperature is 0 Kelvin, is always 0. Got it? Is always 0. When you increase the temperature of such a crystalline substance, which means when the temperature is greater than 0 Kelvin, definitely the entropy will be greater than 0. Greater than 0. In other way, with our simple entropy, the relationship between entropy and temperature on the three phases of a matter is shown here. Got it? Melting, boiling will have the effect of increase in the temperature. See, at absolute temperature 0 Kelvin, entropy begins with 0. Got it? So the solid will naturally exist up to the room temperature without changing its size and shape. So when you melt a solid, which means imagine you are melting ice, then it begins to change its phase from solid to liquid. So the melting will increase the entropy at a particular temperature. Then when you boil such a liquid, say water, then it begins to vaporize. Got it? Begins to vaporize. You know the average temperature of boiling is 100 degrees Celsius. That also increases the temperature. Got it? So whatever it is, the entropy of a pure crystalline substance, if you take a water, means the crystalline form of water is said to be the ice. Okay, so the entropy of ice is 0, because everything is solidified perfectly, or for a perfect solid the entropy is 0, which means the atoms or the molecules will not move a single step to account the randomness. Got it? So these are the values of the standard entropies we account in their standard states. We call it as a molecular entropy of gases, liquids, and solids, which are all very well known for our engineering aspect and its application to account in unit processes. Got it? Which means where the reaction involves. The standard entropy, if you see the trend, the standard entropies tend to increase with increasing molar mass. Whenever there is a molecular weight increases, the number of molecules will increase. So, as we seen already, the number of molecules or number of moles increase in that will increase the entropy. Already we seen in the molecular state of understanding entropy. That is how it has been shown here. Got it? And the standard entropies of a particular gases have been shown here. Larger and more complex molecules have greater entropies. Think about how a methane and the four atomic hydrogen are linked with it. Based on that, the entropy will be decided. Likewise, the ethylene, if you take, or ethane, we'll consider how the three hydrogen atoms are distributed to the two carbon atoms. So the complexity will be increased in the bonding nature of a particular ion with another ion will cause the molecule as a complex one. So whenever the complexity increases, then there will be increase in the entropy in a greater amount. So that if you consider a reaction, that is what our major view, the entropy changes for a reaction can be calculated In a similar way that we have focused on the change in enthalpy as the application of the first law of thermodynamics. So, change in entropy of a reaction is the difference between the sum of standard entropy for all the reactants and the standard entropy of all the products formed. So that is what the individual state, the standard entropies have been highlighted in the previous slide. But for pure elements, pure crystalline substances, or pure elements, not for a pure crystalline substances, pure elements, your change in enthalpy is zero at standard condition, but standard entropy is not zero. So how do we focus on the practical use about the system and surrounding to account the entropy? So already we focused about the change in entropy of the surrounding is accounted as the decrease in the heat from the system to the surroundings in the direction of increasing temperature or decreasing temperature with respect to the temperature or the temperature change, which means the change in entropy will always accounted at a particular temperature only, right? So that surrounding temperature change in entropy will be accounted as the heat, how it is moved or transferred from a system in a direction of decreasing temperature is equivalent to the change in standard enthalpy in the same direction. Change in standard enthalpy in the same direction. That is what these things will be considered. Okay, that means heat that flows into or out of system also changes the entropy of the surroundings. That's what it is given for an isothermal process. It is so at constant pressure. Mean isobaric means this will be considered as a change in the standard enthalpy of the system. Simply, got it. This is how the phase change is isothermal for melting and boiling. If you consider, then for melting, we account it as a change in enthalpy as a fusion in our exact way of understanding that physical nature of melting, which is 6 kilogram per molecule per mole. And for boiling, it will be accounted as change in enthalpy of vaporization, which is 41 kilojoule per mole. So if we do this reversibly, then the change in entropy of surrounding is equal to the negative of the change in entropy of system, because for reversible process the net change in entropy is zero. By making use that expression only, it is being rewritten or re-expressed like this. Then already I mentioned about the entropy change in the universe. The universe is composed of system and surroundings. So therefore, if you consider the universe, it is the sum of the change in entropy of the system and surroundings. And for spontaneous process, it is greater than zero. Already mentioned, highlighted all these points in the previous things. This is the overall thing. If you consider it, then change in entropy of the universe is equal to change in entropy of the system plus surroundings. Already I quoted expression for the surroundings, which means every term in this expression will be expressed multiplied by temperature, means you will get it as a temperature times change in entropy of universe is equal to temperature times the change in temperature of system plus or minus the change in standard enthalpy of the system. That will be accounted here as the free energy that was given by Gibbs. So it is named as Gibbs free energy, because you will get the negative value. That is why the negative sign is given, because the change in standard enthalpy of the system will have a more uh, negative value. That is why when you rearrange it, okay, when you rearrange it, okay, the standard or the Gibbs free energy now will become the difference between the standard enthalpy change of the system minus the product of temperature times the standard sorry the change in entropy of the system. So with respect to system, we can now define and understand how much free energy is available in the system that we can utilize and interact with the surrounding for its transformation or conversion to perform any energy under thermodynamic state. Got it? This is the fundamental expression for all of our reactions. When we focus on the unit processes, reaction is the deciding factor. So, designing of a reactor is our primary job. In that way, the free energy of the entire reacting system we have to measure, or we should know based on that only the quantity of heat needed to perform the reaction or the mass needed to perform the reaction will be decided by following the simple kinetics. Got it? So the Gibbs free energy is defined as the product of the isothermal temperature along with the change in entropy of the universe. As we are well aware that already I mentioned, for spontaneous processes, change in entropy of the universe is greater than zero. So therefore, change in free energy is less than zero for a spontaneous process, which means Gibbs free energy is easier to determine than the entropy of the change in entropy of the universe. So we have to use the Gibbs free energy to decide if a process is spontaneous. Sometimes, as we all know that measurement of degree of randomness will not give us the accurate result. So in that case, we have to focus on this Gibbs free energy and its change. It is easy to measure when compared with the other thing. I mean the entropy measurement. So if Gibbs free energy is change in Gibbs free energy is negative means the forward reaction is spontaneous. This is the most important significance we should understand. If the Gibbs free energy changes zero means definitely the system or the reaction will reach its equilibrium state. And lastly, if the Gibbs free energy change is positive means then the reaction is spontaneous in the reverse direction. See, the spontaneous concept, which means the instantaneous concept, the concept of reversible and irreversibility, will now summarized with respect to the measurement of Gibbs free energy change. So once again I will highlight, and that is how it is shown for the Haber's process in the picture for the production or the manufacture of ammonia. If we account the Gibbs free energy change in the forward direction, if it is negative means then the forward reaction is spontaneous, which means nitrogen reacts with hydrogen and forms ammonia is an instantaneous one. If the Gibbs free energy is changes zero, then the reaction reaches its equilibrium state. Okay, you can define it very clearly. If the Gibbs free energy change is positive means the reversible part is also spontaneous. So the change in Gibbs free energy change will decide in which way the reaction is spontaneous clearly. Got it? Very, very clearly. That is what shown with the movement of the ions and how it bonds with other ions to form the ammonia. So, the standard free energy changes of formation will now be considered as the difference between the sum of standard Gibbs free energy of reactants along with the sum of the standard Gibbs free energy of the products. So, the Gibbs free energy and its relation, how we have shown in the previous slide, will make us to eliminate the measurement of entropy, which is a difficult one. Okay, measurement of entropy as a difficult one. So if we know the standard entropy and standard enthalpy, we can account this free energy in this way. So this now becomes a very key equation for understanding our reactions and reaction equilibrium. Okay, and this is the equation which shows the how the Gibbs free energy changes with change in the temperature. Then you can decide at what temperature the reaction reaches its equilibrium also. Okay, so the key equation will have a two parts. One is the enthalpy term and another is the entropy term. So the temperature dependency of free energy comes from the entropy term only, not from the enthalpy term. So these are the given values for the known or the significance of the Gibbs free energy change to decide the reaction characteristics. Say for example, okay, from ozone to oxygen or oxygen to ozone, and vice versa of the solid liquid to solid and solid to liquid formation of the water. Everything is shown here with respect to the Gibbs free energy change. Okay, free energy and equilibrium. This is most another important thing to account or to find maybe the equilibrium constant. So if your fixed energy change is zero, then the system is at equilibrium. So the Gibbs free energy change must be related to the equilibrium constant K. The standard free energy change is directly linked to equilibrium constant as shown below, which means the standard free energy change is given by negative times the universal gas constant times the temperature times the logarithm of the equilibrium constant. Okay, so based on the value of K only, it will be decided whether the change in standard Gibbs free energy is negative or positive. Based on that, you can decide in which direction the reaction is spontaneous, either in a forward direction or in a reversible direction. This is another key equation to account the equilibrium state. So under non-standard conditions, we need to use change in Gibbs free energy instead of the change in the standard Gibbs free energy. So here is the relation between these two quantities along with the reaction quotient. The reaction quotient is simple to understand. The K, the equilibrium constant, will varies with temperature. Okay, so K at standard state divided by K at the given temperature state. That is what the reaction quotient is. Our main target will be to account the reaction quotient to find the equilibrium constant and how it is related to the your temperature and all. That matters the kinetic studies of every reaction either as a first order or a second order and so on along with the different reactors. Okay. Away from equilibrium, the sign of your Gibbs free energy change tells which way the reaction goes spontaneously. Already we highlighted about it. very clearly. If it is negative, the forward reaction is spontaneous. If it is positive, the reverse reaction is spontaneous. So, this is what the overall view of the application of the three different laws of thermodynamics and how it is accounted to our chemical engineering to understand the concept of the chemical reaction and its equilibrium finally. Got it? Because these concepts will decide the entire design of our unit operations in chemical engineering. So that is why this presentation will give you the most valuable information about the thermodynamics and the thermodynamic aspects of chemical reaction engineering as a part of the unit processes. Thank you very much, my dear students. Thank you.